Okay, hello everyone. Are you able to hear me? Just say yes in the chat if you can hear me and then we'll move on. Okay, if you can't hear me then just refresh your screen if you can't hear me. Okay, now let's move on. So on the AMC 10 and 12, one important concept is Simon's favorite factoring trick, and it's an example of a D'Hoffmann equation, and we covered that concept yesterday, and you're gonna think they're both pretty similar. And you can identify Simon's favorite factoring trick when you have when you have one term which are basically two variables multiplied, and then two linear terms which are just two variables standing alone. And if that's the case, then you can use Simon's favorite factoring trick. For example, this is a basic example. Find the positive integers x and y such that xy plus y equals to 20. Now the way to solve such a problem is you first take like the term with two variables and then another linear term. We'll take x for example, and then you factor those two terms. You get x times y plus 1, and then you want y plus 1 over here also, and you multiply this by the term that gives you this other term here, this linear term, and clearly you have to multiply this by 1. But if you do so, then you get, and if you expand this, you'll notice that you have an extra 1 here. That means you add an extra 1 to the right side, which gives equals to 21. And in this case, you can factor this by adding the x and 1, which gives x plus 1 times, x times x plus 1 times y plus 1, which equals to 21. And then you can use, and then you can take the see 21 is just 3 times 7, and it's also 1 times 21, and it's also 21 times 1, and it's 7 times 3. And then you see, and then you go in order, like take these as the x terms, all the way, these 4 terms are x, and then these y's. So then 3, you add, how do you get 3 from x plus 1? Obviously, just subtract 1, 2. Same here, 7, you need 6 here to get 7 here. And you do the same here, 0. And then you get 20 here. However, this is not a case because it says positive integers, and 0 is not positive. So this case does not count. Then you take 21 and 1. You get 20 for x and 0 for y. However, this does not work because it says positive integers, which means none of them can be 0. You need to remember that part. And for 7 and 3, we get x as 6 and y as 2, which means there are just and then this is that means there are only 2 cases for it. There are only 2 cases for it, and that's how we found the answer. And now we're going to solve this problem, which will be a bit more challenging. Okay, so the problem reads, a rectangular floor measures a by b feet, where a and b are positive integers with b is greater than a. An artist paints a rectangle on the floor with the sides of the rectangle parallel to the sides of the floor. The unpainted part of the floor forms a border of width 1 foot around the painted rectangle and occupies half of the area of the entire floor. Now, how many possibilities are there for A and B? So for such a problem, you make a diagram first to make it a bit easier to understand. And then we have a rectangle here. And it says that the artist paints the rectangle floor so it forms a border. So the floor is actually this area. So this is the flooring we have, this smaller rectangle inside. And it makes a border of 1 feet. That means this is 1, and this is 1. Now, the problem also tells us that B is greater than A. So this is B, and this is A. Now, we want to, and then it also says that the area of the painted rectangle that occupies half of the area of the entire floor. And now we know that the dimension of this whole thing is b minus 2, because we know this is 1 and this is 1. So you just subtract those two from b, and you get this dimension as b minus 2. And you do the same for a, and you get a minus 2. Then we will now it says that that b times a is double of this. That means if you multiply this area by 2, you get b times a. So ab equals to 2 times a minus 2 times b minus 2. Now, if you solve this, you get ab equals to 2ab minus 4a minus 4b plus 8. And now you subtract, you take ab to this side, you subtract ab from both sides, and you get ab minus 4a minus 4b plus 8 equals to 0. And now we have a term which has two variables and two linear terms. So clearly, we just use Simon's favorite factoring trick. So we'll take these two terms, and these two terms factor as a times b minus 4. Now Simon's favorite factoring trick works if the next thing also, we have a b minus 4 here. And for this, we need to multiply it by negative 4. So we can get negative 4b. But clearly, if you do that, you get an x, and we'll also take 8 to the other side. So we subtract 8 from both sides, and you get a times b minus 4 times b minus 4 equals to negative 8. However, if you multiply these negative 4s, you get 16, which means we added an extra 16 to both sides, which means this 8 just is positive 8. And then we have a minus 4 times b minus 4 equals to 8. And now all we have to do is divide 8, and notice that 8 is just 1 times 8, 2 times 4, 4 times 2, and 8 times 1. And now let's try to solve the problem with that information. I'll make some space here. So okay, so for the first case, if a is 1 and b is 8, that means a minus 4 is 1, then a is 5, and you do the same for b and you get 12. And you do the same for the next two terms, and you get 6 here and 8 here. And you do the same for this third expression, and you get 8 and 6 as the values of a's and b's. And you do the same for the last one, which is 8 times 1, which means a is 12 and b is 5. However, the answer is not 4 because it says b is greater than a. B is greater than a here. B is greater than a here. However, a is greater than b here, and a is greater than b here. So the answer is 2 cases. So this shows the importance of Simon's favorite factoring trick, because using that trick, we were actually able to find the answer. So now, this next problem is a bit more challenging. So it's all about variable substitution. So pretend you have lots of variables. Then in that case, you rewrite some of those variables in terms of other variables. If you don't get what I mean, this example should clear it up. And it's from the 2007 AMC 12B problem 23. So it was like a final 5. So here, I'll show you the problem. So it says, how many non-congruent right triangles with positive integer leg lengths have areas that are numerically equal to 3 times their perimeter? Okay, so if we have a right triangle, and the side length, pretend these legs are A and B, and let's say this is C. So it says that their area is numerically equal to 3 times their perimeter, which means the area which is AB over 2, this equals to 3 times the perimeter, which is A plus B plus C. But clearly, if you look at this expression, there are 3 variables. That's going to be kind of hard to solve when you literally have just one equation. But we notice that C also equals to the square root of A squared plus B squared. And then we can substitute that in here to make this expression with only 2 variables. And let's do that. And I'm also going to multiply it both sides by 2 to get rid of this denominator. So if we do that, we get AB equals to 6 times A plus B plus the square root of a squared plus b squared. And still, there are way too many expressions, and it doesn't look like I can apply any factoring techniques because of the square root sign here. So then we have to think of something smarter. And that smart idea comes when you complete the square of a squared plus b squared. And if you complete the square of that, you get a plus b squared minus 2ab. So if you can rewrite a squared plus b squared as a plus b squared minus 2ab. Now we notice we have ab here, and a plus b here, and a plus b here. So let's just substitute variables for those terms. Let's say that a plus b equals to x, and ab equals to y, and see if we can get some success in this problem. Now we substitute those variables in, we get y equals to 6 times x plus 6 times the square root sign, and the square root sign inside we have a plus b squared, which is x squared, minus 2y. Still, now the problem looks a lot easier than this one. This expression was way too confusing. Now, when we have a radical sign, you isolate the radical sign. So if you square both sides, the radical sign just cancels out. So we're going to square both sides after subtracting both sides by 6x. So if you subtract both sides by 6x, you get y minus 6x equals to 6 times the square root of x squared minus 2y. And in this case, now we're going to square both sides to get 36x squared plus y squared minus 12xy equals to, and if you square this sign, you get 6 times 6, which is 36, times these two terms here. So this equals to 36x squared minus 72y. Clearly, if you subtract both sides by 36x squared, they just cancel out. So now we have y squared minus 12xy equals to negative 72y. And clearly, you can divide the whole expression by y. And let's see what we get now. So after dividing the whole expression by y, the y squared becomes y, the 12xy becomes just negative 12x, and the term at the end becomes negative 72, because we divided the whole thing by y. And now, this seems a lot more solvable. Let's just isolate the y and keep it on one side. If you do that, you add 12x to both sides and get y equals to 12x minus 72. And this seems a lot cleaner. So let's substitute these substitutions that we made back into the equation. So y equals to ab. So we can substitute ab back in. So ab equals to 12 times a plus b. 12 times a plus b is just 12a plus 12b. And then we have a minus 72 here. And now we have made Simon's favorite factoring trick the same form that we needed. We have it, and now we can just factor this out. So we know we will just take two terms. AB, this is equivalent to AB minus 12a minus 12b plus 72. And now we can solve this by taking the first two terms, like one linear term and one term with two variables, and you factor the a out, and you get b minus 12. Oh, this is a 12b. Okay, and now you want b minus 12 here also. And this equals to negative 72, because the 72 you just put it back there. And then now we notice, how will we get a coefficient of negative 12b? Well, obviously by multiplying by negative 12. And then we notice that if we multiply by negative 12, we add an extra 144. And we added it to the left side, so we have to add it to the right side. And if you add 1 plus 144 here, this becomes 72. So this at the end, this factors as a minus 12 times b minus 12 equals to 72. Now you look at the pairs of 72. So 72 equals to 1 times 72. This also equals to 2 times 36. This also equals to 3 times 24. This equals to 4 times 18. This is also 6 times 12. This is also 8 times 9. And now we're not going to write 9 times 8 again and 12 times 6 again. The reason is that if you put this back in here in a minus 12 and b minus 12, like pretend we put back 1 and 72, then we get 13 and 85 for a and b. And if you do it for 72 and 1, then you get 85 and 13. But notice that it says non-congruent right triangles, and if two legs of a right triangle are 13 and 85 or 85 and 13, then they are congruent right triangles. So the amount of pairs is just 6, not 12. So this just highlights the power of Simon's favorite factoring trick, because it made factoring and this very complicated problem a lot easier. So now the next problem, which is all about infinite geometric series. Well, an infinite geometric series is basically a series that has a common ratio the entire time and it's never ending. And clearly you know it's never ending because it's infinite. And then the formula above over here, it calculates the sum, and it only works when the ratio of the infinite geometric series is less than 1. It has to be less than 1, the ratio. So in this case, the formula is the first term of the series, a over 1 minus r, where r is the ratio and r has to be less than 1. So the ratio, so if a geometric series has a ratio of 2, then you cannot use this formula. And that's pretty obvious. For example, if I have a geometric series that starts with a 1 with a common ratio of 2, then your terms will be 1, 2, 4, 8, 16. You see, the terms keep going up. You can't calculate the sum of that. That's not possible. You can't even round to it. So that's why the ratio has to be less than 1. So now, this problem is from Amy to problem 11. It's a problem 11. So it says two distinct real infinite geometric series each have a sum of 1, and they have the same second term. Now the third term of one series is 1 over 8, and the second term of both series can be written in this form, where m and p are positive integers, and m is not divisible by the square of any prime. Okay, so we have two infinite geometric series, and they have the same second term. Now, in such a problem, don't be afraid of using variables. So pretend this is the first term, this is the second term, and this is the third term. And this is the first series, and this is the second series. Now in the problem it says that the second term is the same. We don't know the second term. Let's just say it's x. And it says the third term of one of the series is 1 over 8. So let's say this is 1 over 8. And then the second term, now we just want to find the second term. And remember, the common ratio is the same for a geometric series. So let's assume the ratio of the first series, let's just say it's r. So that means x times the ratio, which is r, has to equal to 1 over 8. Now we want to find r in terms of x. Simply you divide both sides by x and you get 1 over 8x. And that is the ratio. And now to find, and then you can check it by multiplying this to x, and you see indeed that is the ratio. And now to find the first term, you just do x divided by the ratio 1 over 8x. And then if you divide it, then you just flip and then you just take the reciprocal of this and you get x times 8x, which means the first term is 8x squared. Now it says we want to find the second term, and clearly we want the value of x. And this can be done using the sum of an geometric series infinite, because we know that the sum is 1. So the sum of an infinite geometric series, a geometric series, it's the first term, 8x squared in this case, over 1 minus the common ratio, which is 1 over 8x. So the ratio is 1 minus 1 over 8x, and this equals to 1. And now 1 minus 1 over 8x is the same thing as 8x minus 1 over 8x, because you take the LCM, which is 8x. And now let's compute this now. And we know this is divided by 8x squared. To make this expression look a lot easier, we can just rewrite this as 8x squared divided by 8x minus 1 over 8x. And then this thing just flips over because you're dividing it. So this just becomes 8x squared times 8x, which is 64x cubed divided by 8x minus 1, and this equals to 1 because that's the sum of this series. And now we can find x by multiplying both sides by 8x minus 1. And after you do that, you get 64x cubed equals to 8x minus 1. And now you subtract 8x from both sides, and then add 1 to both sides, to find a factorable form. So 64x cubed minus 8x plus 1 equals to 0. And usually whenever you have a cubed term and 64 is like 4 cubed, because 64 is 4 cubed, you can usually factor it in a form of 4x times 16x squared. And then after a lot of substitution, you can factor this on your own, but after you substitute, to factor this, you do some trial and error, and after you do, you get 4x minus 1 times 16x squared plus 4x minus 1. And we said that this is equals to 0. 0. And then the value of x for 2 equal to 0, you just set this term equal to 0. So 4x minus 1, if that equals to 0, then we know x equals to 1 over 4. However, it's in the form of square root of m minus n over p. So this is not possible. Now we'll test the other part, which is 16x squared plus 14x minus 1. When we set that equal to 0. And then this is just a quadratic. This is literally just a quadratic. So we know negative b plus minus square root of b squared minus 4ac over 2a. That's the formula. And this is b, this is a, and this is c. So you substitute the values in. And then b squared, which is 16, minus 4ac, the minus cancels out, plus 64 over 2a. And then that's 2 times 16. And then this simplifies to negative 4 plus minus square root of 80 over 32. And now let's reduce the terms. The negative, we clearly see that 80 is just 16 times 5, which is negative 4 plus minus 4 times the square root of 5 over 32. And then we see the 4's cancel out because with the 8. So we get negative 1 plus minus square root of 5 over 32. And then we notice this is the exact same thing as this, except in this expression, the square root term comes before the negative term. So it's just square root of 5. And then we have negative 1 here over 32. And now we want to find 100m. So we multiply 100 times just 5 to get 500. And then this is actually 8 because the 4's cancel this out to 8. So this is, the denominator is 8. Okay, and then now it says n, and you multiply that by 10. And clearly n in this case is just 10. So 500 plus 10. And we take the denominator alone, which as 8, so 8. And then 500 plus 10 plus 8 is 518, which brings us to our answer. So this shows the power of knowing the formula for the sum of a geometric series infinite, how we were able to crack out an AMC problem 11. The next problem, and manipulation. Sometimes when you have like so many variables, you can't really kind of like factor this and find the answer like a system of equations because there are way too many variables, and the number of equations you have is less than the variables. So then you have to do something clever, or else you won't be able to solve the problem. And the cleverness comes from by literally like manipulating the equation. You either add them, you subtract them, or try out what to do. So in this question, we have these two equations, and a is greater than b, and b is greater than or equal to c, and then these two equations, and we want to find a. So let's write them down and see if we notice something. So a squared minus b squared minus c squared plus ab is equals to 2011. And the other one, a squared plus 3b squared plus 3c squared minus 3ab minus 2ac minus 2bc, and this equals to negative minus 1997. So you might be thinking that, oh, if I subtract this, the a terms cancel out, and then we have one less thing to deal with. However, you still have so many variables to deal with, and that's not going to make a difference. If you have like 100 variables and you remove one, that's not going to help. So that's not the way to solve the problem. Now we tried subtraction, that's not going to help. Let's think about addition. The coefficients, this becomes 2. The negative plus 3, 2. The negative plus 3, 2. the a minus 3, negative 2, this is still negative 2, and this is negative 2. That means if we add it, the coefficients for the whole thing is just 2 times a squared plus b squared plus c squared minus ab minus ac minus bc equals to, and if you subtract this, you get 14. Yeah. So this looks a bit easier to deal with. However, we notice we have an a squared and a b squared and a c squared and an ab and an ac and a bc. What if we can factor it out into forms of a minus b squared, b minus c squared, or a minus c squared, something like that. So we know we can. So the terms we want, a squared plus b squared. We're gonna rewrite this now. I'm gonna rewrite it to make it look a lot easier for you. So we have this a squared plus b squared minus 2ab, because 2 times ab, we know that's 2ab, and we have another a squared and another c, and then we have another a squared plus c squared, and then we have minus 2ac, and then we have another b squared, and we also have another c squared that we didn't add yet. So b squared plus c squared minus 2bc equals to 14. Now if you squint at this problem, you'll notice you have a squared plus b squared minus 2ab, which is a minus b squared. And then you also have a plus c squared minus 2ac, which is simply just a minus c squared. And you also have b squared plus c squared minus 2bc, which is b minus c squared. And all of this equals to 14. And we know that these are integers. So whatever these expressions are, at the end, all of these are perfect squares. So now we have to think about what adds to 14. 3 numbers that add to 14, and they're all perfect squares. And if you try, do some trial and error, you'll notice 9, 4, and 1. They add up to 14 and are perfect squares. So that's perfectly and exactly what we need. Now, how do we know which one's which? Clearly, A and C, they're the farthest apart, which means that A and C will have the biggest difference, which means A minus C equals to 3. Now, if you actually solve the problem, you will assume first that A minus B equals to 2 and B minus C equals to 1, because like this, or you'll do A minus B equals to 1 and B minus C equals to 2. So if you do that, you have two cases, but we will assume that B, this thing over here, we'll assume this is 1 and this is 3. B minus C equals to 3. Yeah. So if you solve for this, you get that this is just A minus 1. That B equals to A minus 1. And A minus 1, yeah, in terms of A. And if you do the same thing over here, you get C equals to A minus 3 because of this thing, you see? And for the A term, you just leave A alone. And then you can put this back into this equation. And then after you solve it, because we don't have enough time to actually solve it here, because you do see, if we put these back in here, it's going to be a lot of algebra. But if you do it, you get 7, 8 equals to, for one of the cases, you get 7, 8 equals to 20, 21. And if you divide 21 with 7, that is not an integer. So clearly, that is not going to be the answer. And if you try the other case, you get 8a equals to 2024. After the computation, we're skimming through the computation because we have to go through other concepts. And if you do 8a equals to 2024 and 7a equals to 2021, which will be our two cases, and then clearly this is not an integer, and our answers are all, we're dealing with integers, but 8a equals to 2024 brings in 253. So that's our answer. But then this shows that when you have so many variables, you try to manipulate the equations by either adding them or subtracting them. And clearly there was symmetry because everything, 2 times all the terms, they were all multiples of 2. So Vietas, for a normal trinomial, the sum of the roots is just negative b over a, and the product of the roots is, no, not negative c over a, I meant positive c over a, sorry. So the product of the roots is just positive c over a. And remember that for any polynomial, the sum of the roots will always be negative b over a. One thing that you should know is that, pretend if I have a polynomial like ax cubed, plus bx plus c. If you think that the sum of the roots is just negative b over a, you're completely wrong, because there's an imaginary x squared term sitting there, like this, plus 0x squared. That's the term over here. It's just hiding there. So the sum of the roots is actually 0 over a, and anything like that, if you're like 0 over any number, it's obviously 0. So the sum of the roots in that case is 0, not negative b over a. So so for a polynomial, pretend you have like ax cubed plus bx squared plus plus bx squared plus cx plus d. So the sum of the roots will be negative b over a. Now pretend the roots are r, s, and t. Now if you want to find the pairwise sum, like rs plus st plus rt, then you look at the second, the other coefficient, at the second one in this case. I mean the third one, and it's that over the first one, which is c over a. And if you want to find the multiplication of all the roots, then you look at the last expression. And an easy way to remember this is you write a negative here for the second term, and positive here and negative here to know what sign you're using. For example, you'll use negative b over here, positive c over a here, negative d over a here. And Vieta's is a concept that is much easier to understand when we demonstrate it with an example. So let's do that. So this is a problem from 1984, the US AMO. It's problem 1, and it reads, in polynomial x to the power of 4 minus 18x cubed plus k times x squared plus 200x minus 1984, and this equals to 0. And it says the product of two of its roots is negative 32. Now it's asking us to find k. So now for this problem, we can't just stare at it clearly. That's not going to be a solution. So we'll use Vieta's formula. Let's say the roots are a, b, c, and d. Usually, if you have a polynomial which the highest degree, like it's 4, then there will be 4 roots. If it's 2, then it will be 2 roots, unless there's a double root. But let's not worry about that right now. So in that case, it says a times b. We'll first write the sum of this. A plus b plus c plus d. It's always negative b over a. So we'll just write negative here, negative here, and positive here. So we know what we're actually computing. And negative b over a is just 18. And now we want the pairwise sum. ab plus ac plus ad plus bc plus bd plus cd, and this equals to k, because positive k over the first exponent. And then if you want to find like abc, like 3 pairs at a time, then you look at the next term, which is 201. And if you want to find all of them multiplied, you look at the last term. After some practice, this will make a lot more sense to you, and you'll find some practice problems for each concept in the handout. But for now, let's solve the problem. Plus bd plus cd, and this equals to k. Now if you want to find the pairs of 3, we have ABC, we also have BCD, we have ABD, and we have ACD, yep. And this equals to negative 200 over the exponent, I mean the coefficient, which is just negative 200. Now we look at the next part. The multiplication of the roots is just positive times negative, so which is just negative 184 over 1. So a times b times c times d equals to negative 1984. Clearly, the product of two of the roots is negative 32, as it says. We can assume that those two roots are just a times b. So in that case, we see that ab times cd, and ab, we know that's negative 32. And if you divide both sides by negative 32, you get the value of c times d, which equals to negative 1984 divided by negative 32. And this equals to 62. We know that the negatives cancel out, and you can do the computation on your own. That means CD equals to 62. And now the equation at the top, let's see if we can use these terms that we have to make our equation look a little neater. So if AB equals to negative 32, we have an AB term here. So let me erase this and write negative 32 here. Okay, negative 32 plus AC plus AD plus BC plus BD plus CD, we have CD. So let's replace the CD with 62. And now we will look in our other equation. Oh no, let's first simplify this out. And if you simplify this, you leave all the variables on one side. You get AC plus AD plus BC plus BD equals to K minus 30. And now we can factor this kind of using Simon's favorite factoring trick, technically a bit. So we have just A times C plus D, A times C plus D, and over here we have B times C plus D plus B times C plus D, and we see that the A's and B's just add up. So it's actually just A. So I'll write this down with text instead. So now we have A plus B times C plus D equals to K minus 30. Still, we haven't gotten anywhere with this. And remember, in one of our previous problems, we substituted the variable like these expressions for more variables. So let's do that here. Let's say that A plus B equals to P, and C plus D equals to, let's say, S. So now this expression just becomes P times S equals to K minus 30. And now, if we look at our other equations, maybe we can plug in A, B, and C, D there. So we already did it for this. We can cross this out. We're done working with that. But if you look at this one, maybe we can get some, maybe we can substitute something in here by factoring first. So we notice that there's an AB term here and an AB term here, and that means we can factor that. So let's do that now. So that means AB times C plus D here plus BCD and ACD. The CDs are common. That means we can factor out the CD plus CD times and A plus B over here. And this equals to negative 200, as we already know. We already have the values of AB and CD from before. Remember, A times B was negative 32, and C times D was, let me write it down here. What was it? Okay, yeah, that was 62. Yep. So 62 was here. So now we can substitute what we had here into this equation. That means negative 32, which is AB, and C plus D, we assumed it was S. So negative 32S plus CD, which is clearly 62 as we rewrote it, 62 times P equals to negative 200. And now we might be able to calculate the expression now. So we do have two expressions. We also know that P plus Q, we also have A plus B plus C plus D equals to 18. That's just the same thing as A plus B plus C plus D, like in brackets, to make it clear that we have AB as P and C plus D as S, which means P plus S equals to 18. And now we have two variables and two equations. P plus S equals to 18. And 62P minus 32S equals to negative 200. Now to solve such a problem, it's a system of equations. You multiply it by either 32 or 62 to cancel out one of the variables. And we're going to skim through that part. After you do so, you'll get P equals to 4 and Q equals to 14. And we want to find K. And from this expression, P times S, we know that P times S equals to K minus 30. And P times S. Yeah, so P times S equals to K minus 30. And P times S is 56. So 56 equals to K minus 30. You add 30 to both sides to get K equals to 86. I know this problem must have been hard to understand, But to learn a concept, you always learn it better by doing a harder problem, because then you will know how to solve the easier ones if you can do the harder ones, which is why we chose to use USAML problem to show VNs. For this problem. Now for sometimes in complicated algebraic problems again, the solution comes by substituting variables in it. You try to make an equation with only one variable, and then you can do this with substitution. For example, if you have a plus b, then you can just make that equal to a variable like x, which makes the problem look a lot more satisfying. For example, now this problem is from the 2000 AMC 1, problem 7, and suppose that x, y, and z are three positive numbers that satisfy the equations x times y times z equals to 1, x plus 1 over z equals to 5, and y plus 1 over x equals to 29. And we want z plus 1 over y equals to m over n, where m and n are relatively prime integers, and we want to find m plus n. Now, we notice that we have a y term here and an x term here. Maybe if we can write this x term as a y term, we'll find the value of y. For that, we have an x term here. For that, we need z to be as a y term, or an x and a y term. So we want to eliminate z and get x, y there, or x, or y separate, because we want a y term here. We want two y terms here, so we can calculate the value of y, which we need. So let's try this. So we know that z equals to 1 over xy, because you can just divide both sides by xy. And using this information, we can also now instead, if you want to substitute 1 over z, I'll just show you an easier way for that. So if we have x, y, z equals to 1, if you want 1 over z, just divide both sides by z, and you get x, y equals to 1 over z. So we have x plus xy equals to 5. So x plus x over y, So we have, I'll just write the whole thing down. So we have x plus xy equals to 5. And this factors as x times 1 plus y equals to 5. Now we want to find the value of 1 over x, so we can substitute that in there. And this can be done by first dividing both sides by x. 1 plus y equals to 5 over x. Now you divide both sides by 5 to get rid of this 5 here. And you get 1 plus y over 5 equals to 1 over x. And we got 1 over x here. Now if we substitute this in there, we can get the y term. And let's do that now. Y plus 1 plus y over 5 equals to 29. Now we multiplied both sides by 5 to get rid of the denominator. So this y times 5 just becomes 5y. The 5 cancels out with the 5. So 5y plus 1 plus y equals to 29 times 5. And 29 times 5 is just 145. 6, and then 5y plus y becomes 6y equals to, and you subtract 1 from both sides, you get 6y equals to 144. And if you divide this by 6, you get y equals to 24. Now we found one of the variables, so now you will find the whole thing. So in this expression, now we want to find z plus 1 over y, and y is 24. So z plus 1 over 24. And now to find y, we can just substitute the y in there, in the expression of this, in this expression. So we can find x and then put this back in there. No, we already have a y term, never mind. We have this term. So we can, instead of actually finding it, we can just substitute this in here. So we get 1 plus 24 equals to 25 equals to 5 over x. And then you multiply both sides by x, and then you divide both sides by 25 to get x equals to 1 over 5. And now if x equals to 1 over 5, you substitute this into this equation to get 1 over 5 plus 1 over z equals to 5. Now you subtract both sides by 1 over 5 to get 1 over z equals to 5 minus 1 over 5, which is just 24 over 25. Wait, is it? No, it's not. It's 124 over 125, sorry. And now, wait, I accidentally made a mistake here. Sorry. So if you subtract both sides by, so you get 1 over z equals to 5 minus 1 over 5. And if you take a common remainder, you get 24 over 5. and then you multiply both sides by z to get 1 equals to 24z over 5. Then you multiply both sides by 5 to get 5 equals to 24z, and then you divide both sides by 24 to get z equals to 5 over 24. And then all we want is 5 over 24 plus 1 over 24, which is 6 over 24. However, we reduce this to get 1 over 4, and we want m plus n. So 1 plus 4 is clearly 5, but this is the AIME, so you write 2 zeros. 0, 0, 5. So this shows the power of trying to substitute even more into the equation that we already have. So now, the next problem. So a lot of problems in recursion can be solved by looking for patterns. You write out a few terms and look for patterns like factorials, addition, multiples, even Pascal's triangle, which we'll learn in a bit. So this is from the 2008 AIME2 problem 6. So the problem says that the sequence ace of n is defined by ace of 0 equals to 1, ace of 1 equals to 1, and ace of n equals to ace of n minus 1. So instead of actually reading this out, let's try to find some of the terms and look for a pattern, because we want ace of 32 and b of 32. So let's look. So we have to find ace of 2 is equals to ace of 2 equals to ace of 1 plus ace of 1 squared over ace of 0. And if you solve this, you get the 1, you substitute the 1 there, and then you just get 2. Ace of 2 equals to 2. Now ace of 3. Now ace of 3 equals to ace of 2 plus ace of 2 squared over ace of 1. And we know these values because of this the expression that they've given us already. So we just use that to find it. And now if you solve this out, you get, yeah, this is ace of 2, yeah. So we know 2 is 2, ace of 2 is 2. So ace of 3 equals to 2 plus 2 squared, which is 4, over ace of 1, which is 1. So ace of 3 equals to 6. Now let's look at ace of 4. Ace of 4 equals to ace of 3 plus ace of 3 squared over ace of 2. And this value is just ace of 3, which we know that is 6 from this. So 6 plus 6 squared, which is 36, divided by ace of 2, which is clearly just 2. So 6 plus 36 over 2. And 36 over 2 is 18, so ace of 4 equals to 24. And now we have found a significant amount of answers in terms. Well, let's look for a pattern. Remember, I said it can be a factorial, it can be an addition, it can be multiples, etc. And actually, you can use some algebra to actually find. You can use algebra to find rewrite this, but sometimes you just look for a pattern to find the answer, and generally that's the most preferred approach. So in this, if ace of 2 equals to 2, there's clearly no pattern with addition or something. So we look at factorials. 2 factorial equals to 2. We have 3 here. Let's see. 3 factorial equals to 6. And we have 4 factorial, and 4 factorial equals to 24. And these match with these terms here, which means whatever ace we want, ace of n equals to n factorial. And we want ace of 32, which is just 32 factorial. Now let's explore the b terms. Now we just look for a pattern, and clearly the b terms look pretty similar to the a terms. So it's going to be related to factorials most likely. Let's look. So we know b of 1 equals to 3. So we know b of 2 equals to b of 1 plus b of 1 squared over b of 0. Now, the reason why recursion can be fun is because at the end of the day, if you look for a pattern, you will most likely find the answer. So we have this, and we know b of 1 is 3, so b of 2 equals to 3 plus 3 squared, which is 9, divided by 1, which is just 9, yeah. So b of 2 equals to 12. And we also have b of 1 equals to 3. Now we look at b of 3. And and then b of 3 equals to b of 2 plus b of 2 squared over b of 1. And now we will substitute the values that we have. We have b of 2 as 12, so b of 3 equals to 12 plus 12 squared over 3. So 12 squared is just 12 squared over 3, which is the same thing as 4 times 12 after you reduce it, and you get b of 3 equals to 60. And sometimes you should pause when you're using recursion and look for a pattern between the numbers you have. And we also know that b of 0 equals to 1. So how do you get to b of 1 equals to 3? Well, you multiply this by 3 to get it. How about 3 to 12? You multiply this by 4. How about 12 to 60? You multiply this by 5. So now this seems like a multiplication that keeps on happening and happening again. So this seems like something similar to factorials. We know that and 3, and then sometimes in these problems you have to go very deep. How like we know that like for factorial, we need to compare this to factorials. So 4 factorial, that is 24, and that seems like that's double the b of 2. This is double that. Now let's look at 5 factorial. 5 factorial is 120, which is double the b of 3 term. That means we have found the pattern. For any b of n, the term we want is n plus 2 factorial over 2. And we found this by just looking at some of the terms. We looked for patterns, and then we found the answer. And clearly we want 32. So we substitute, so b of 32 equals to 34 factorial over 2. And now we just have to solve this. So 34 factorial over 32 divided by 32 factorial, which is the same thing as times 1 over 32 factorial. So now 34 factorial divided by 32 factorial is just 33 times 34. Yeah, this is a 2. So this is just a 33 times 34 over 2, which is, the 2 reduces to 17 with this. So our answer is just 33 times 17, which is 561. So this shows the power of looking for patterns in recursion between the numbers, between the term, and maybe you'll get the answer by looking at patterns. And this was a problem 6, and we cracked it out. So now our next thing is about completing the square, which is an overpowered method of factorizing, which can be very helpful in some problems. A basic worked out example is below this. So to factor this, you take the term which has like no variable in it, and you isolate it to one side. So we did this here. After that, you want to find a term such that, like, you know you're going to square this, right? You want a term such that 2 times this variable, whatever number here, 2 times this number times x brings in 6x. And clearly 3 is the only thing that makes 2 times 3 times x as 6x. And you make this the addition sign. And then you see that for this to be true, you have to add 9 to both sides. And if you add 9 to both sides, the negative 8 becomes 1. And then you just get x plus 3 squared equals to 1. And if you square root both sides, you get x plus 3 equals to plus minus 1. And then you can just set x plus 3 equal to 1 to get x equals to negative 2. And you can also set x plus 3 equal to negative 1 to get negative 4. So this shows that completing the square can be pretty powerful in mathematics. So in this problem, there exist unique positive integers x and y that satisfy the equation x squared plus 84x plus 2008 equals to y squared. Now we want x plus y. Now clearly, if we want to use completing the square, we're not going to use it with y squared because we have no term with just y in it. But we do have that term for x. And clearly, to get now we're going to isolate. Now we're just going to put the x terms on one side and throw everything to the other side. So if you do that, you get something that looks like this. Now, to solve this problem now, we will complete the square for x squared plus 84x. And for that, you get x plus 42 squared, because we want it such that 2 times x plus 42 equals to 84x. And clearly, 42 squared is just 1764, I think. Yeah, so 1764. That means you add 1764 to both sides, and then if you add 1764 to 2008, that it just becomes minus 244. So now this looks a lot more simpler than this equation up here. Now that we have reached this point, the way to solve the problem is to bring the x plus 42 squared to this side. I will show you why. And the 244 to the other side. If you do so, you'll get y squared minus x plus 42 squared equals to 244. And this is pretty much similar to the difference of squares, because if you take x plus 42 as like a variable z, then it's just y squared minus z squared. And then if you do that, you can just literally factor this out as y plus x plus 42 and y minus x minus 42. You can literally factor it out in this way. And this equals to 244. Now to solve the problem, you need to break the 244 and realize that it's just 2 squared times 61. Now we know that the factors must, now we need to think about the problem a little bit. We notice that this is like, if we take this separate variables like y minus x minus 42, we write this here. I will show you why in a second. And we don't know what these are equal to. Let's pretend this is equal to 2, let's say this equals to 4 and this equals to 61. Then if you add these two things up, you get the 42's cancel out, the x's cancel out. You get 2y equals to 65. And if you divide by 2, it's not an integer. And if you want to divide something by 2 to get an integer, it has to be an even number. And that means y and x have to be an even number. These two, this term and this term, that has to be an even number. And that will only work in the case of 2 times 122. And now we have found out what we want. And we know that y minus x minus 42 is 2 and not 122 because this is the smaller term. Obviously, you're subtracting things from it, so it's obviously going to be smaller than this term. So y minus x minus 42 equals to 2. And above, we have y plus x plus 42 equals to 122. Now, if you add both of these equations up, the x's and the 42 cancels out. So you get 2y equals to 124. You divide both sides by 2 to get y equals to 62. Now, we can just substitute a y into one of these equations, and 62 plus 42, 104. You subtract 104 from both sides to get x equals to 18. And that means we want x plus y, which is 62 plus 18, 80. But this is the aim, so don't forget the 0. 0, 8, 0. And that is our final answer. So this shows the power of completing the square, and it can help you in a lot of problems. So our next problem. We know that a geometric series, it has a common ratio. For example, pretend the first term is a, then we know the next term is a times r, and the next term is a times r squared. But there is one rule that is not as well known. It's basically a pattern that you can find out even while taking the test, but it's hard to find something out while you're taking the test, so it's better to know it from before. And it states that if you take, pretend the sum of the first two terms and the sum of the next two terms, pretend this is the first term, this is the second term, this is the third term, this is the fourth term, and this is the fifth term, and this is the sixth term. So this states that the sum of the first two terms and the sum of the next two terms and the sum of the next two terms, you can keep on going on, but the sum of those will be in the same ratio no matter what. For example, I'll show you an example. If I have a geometric sequence where the first term is 1, the next term is 2, the next term is 4, the next term is 8, the next term is 16, and the next term is 32. So what I mean is that you can even take the first three terms and compare it with the next three terms and compare it with the next three terms after. The ratio will always be the same. But I'll show you for the first two terms. So the sum is 3, the sum of this is 12, and the sum of this is 48. Notice this is just 3 times 4, which is 12, and 12 times 4, which is 48. So that means the ratios of the sums are also the same. And now let's use this to find the answer to this problem. It says, the sum of the first 2011 terms of a geometric sequence is 200. The sum of the first 4,022 terms is 380. Now we want the sum of the first 6,033 terms. As of what I said, if you take the sum of a certain amount of numbers, like in x terms, the sum of first x terms, this will be then the sum of the next x terms, and then the sum of the next x terms. This will always be in the same ratio. And in this case, the sum of the first 2,011 terms is 200. The sum of the next 2,011 terms is actually 180, because 380 minus 200, 180. And now we want to find the sum of the next 2,011 terms to get 6,033. And now, as I said, the ratio will be the same. To go from 200 to 180, you multiply by 180 over 200, which equals to 9 over 10. That means to go from 180 to the next 2,011 terms, you multiply by 180. You multiply 180 times 9 over 10. And after you do so, you get 162. That means the sum of the first 2,011 terms is 2,011. The sum of the next 2,011 terms is 180. And the sum of the last 2,011 terms is 162, because the sums are also in the same ratio. And if you add these three numbers up, you will get 542, which is the answer. And now the next problem, which is related to arithmetic sequences. Now an arithmetic sequence is just where, like, pretend the first term is a, and the next term will be a plus r, then the next term will be a plus 2r. Like, the common difference between any two consecutive terms is always the same. And then you use like some terminology in this to write it in an algebraic form, which can be very helpful in some problems, which are pure arithmetic sequences. So now it says, find the 8th term of the sequence 1440, 1716, 1848, whose terms are formed by multiplying corresponding terms of two arithmetic sequences. For example, if this is the first term, and this is the second term, and this is the third term, that means the first term of one arithmetic sequence. For example, pretend I have two arithmetic sequences. This is one of them. This is A1, ace of 1, and ace of 2. Two arithmetic sequences. And the first term is x. Let's say it's A, and this is B. The common difference, let's say it's D. So for this one, A plus D is the second term, and for this one, B plus, let's say C. And then the next term is going to be A plus 2D, and then the term after will be B plus 2C. And we want to find the 8th term of this sequence, which is the multiplication of these things. And the 8th term will just be A plus 7C times B plus 7C. And if you expand this, you get AB plus 7C. 7D times plus 7C. Sorry, this is D. So if you expand this, you get AB plus 7AC plus 7BD plus 49C squared. 49CD. Yeah, 49CD. Now to solve this problem, we know that the first terms of both of the sequences multiply to the first term of this sequence. So we know AB equals to 1440. So AB equals to 1440. Now, the next one. The next two terms multiply to 1716. So A plus D times B plus C is just AB plus CD plus BD plus AC. And this equals to 1716. And we know AB, that is 1440. Yeah, 1716. So 1716 minus 1440 gives us 276. So this is just CD plus BD plus AC equals to 276. And now to find the answer, we will if you expand the first term, and now if you multiply A plus 2D times B plus 2C, and you also substitute AB in, and then you subtract it from 1848, you're supposed to get Yeah, let's just solve it first. AB plus 2AC plus 2BD, because you're multiplying these two things as two equations, and then you'll get AB plus 2AC plus 2BD plus 4CD. And then we know that this if you actually calculate this out, we know AB AB is 1440, and you subtract that from 1848, and you get 408. And now we're actually going to leave this problem here because we have to move on to the probability and combinations part, because there's a lot to cover there. But this problem can be solved because after you solve these equations here, you can literally subtract the terms and find each individual term and substitute it for AC and BD and CD. But I'll add this problem to the handout for you guys to solve. We need to cover logarithms very quickly. So for a logarithm, since some people taking the AMC 10 might not know what logarithms are, we'll convert this expression full of logarithms into exponential form so everyone can understand. Okay, so for logarithms, now since the people taking the AMC 10 might not know what logarithms what this means, I'll convert this for you guys. So like 2x to the power of n equals to 3 to the power of 20, and 2x plus 3 to the power of n equals to 3 to the power of 2020. Okay, now we have converted this into exponential form, so now everyone will be able to solve it now. So if you look at the equation 2x, so these the exponents just multiply out because of the logarithm rules and the exponential rules. We know the exponential, not 2020. Okay, so now for the problem, if you actually divide both expressions, I mean substitute 3 to the power of 20 here. You substitute 2 to the power of x times n, which is 3 to the power of 20, into this second equation. You get 3 to the power of 20 times 2 to the power of 3 of n equals to 3 to the power of 2020. And now if you divide both sides by 3 of 20 to isolate the variable term, the exponents cancel. The exponents just subtract out. So 2 to the power of 3 of n equals to 3 to the power of 2000. Now you might be wondering about how you're supposed to solve the problem, but remember, we want x of n. So maybe if we can, for this case we have n here. Maybe we can find x by looking at this number here, but for that to be true, we have to take the 100th root of both sides to get 3 to the power of 20 on the right side. So if we do that, we have 2 to the power of 3 and divided by 100 equals to 3 to the power of 20, and that's where we finally find our answer, because we have 3 to the 20 and 3 to the 20 here. So if we set these equal to each other, we have 2x of n equals to 2n multiplied with 3 over 100, and this is supposed to be these two things are supposed to be equal to each other. We see the n's are equal, obviously, and then we have x equals to 3 over 100, which is just 100 plus 3, because we have to find m plus n. That's why you should read the problem, and that's where you find the answer. Now the next problem is pretty simple. I just wanted to show a basic example of inequalities before we move on to probability. So a lot of inequalities will appear in word problems, and you can crack them out by turning the word problems into inequalities or equations. And you can solve an inequality by multiplying or dividing or subtracting and adding in normal ways. However, just remember that if you multiply or divide by a negative number, then the sign will flip over. For example, if I have x is greater than or equal to negative m is greater than negative 2, and if I divide it by negative 1 from both sides, the answer is not x is greater than 2. It's actually x is less than 2, because you flip the sign over. So now let's solve this problem to show the example of inequalities. A tennis player computes her win ratio by dividing the number of matches she has won by the total number of matches she has played. At the start of her weekend, her ratio is exactly 0.500. This means if she has won in X amount of games, then she has played 2x amount of games, because the ratio is 0.5 as the problem states. And now it says, during the weekend she plays 4 matches, winning 3 and losing 1. So she wins x plus 3, and the amount she plays is 3 plus 1 plus 2x, which is 2x plus 4. And this ratio is greater than 0.503, and we'll convert this into fractional form, which is 503 over 1000. Now you can simply multiply 1000 to both sides, and then 2x plus 4, and without flipping the symbol, because you're not multiplying or dividing by a negative number. So after you do that, you get 1000x plus 3000 is greater than 1006. Yeah, 1006x plus 2012. And then you can subtract both sides by 6 to get 6x to get negative 6x is greater than this 2012 minus 3000, which is just negative 988. Now clearly we need to divide both sides by negative 6 to get rid of the negative signs, and if you do so, the signs flip over. So now we need to compute this, and after you solve this, we see that the negatives cancel out, and 988 over 6 is it's a little more than 164. It's like 164.7, but x has to be less than this, and we want to find the greatest number of x that is less than 164.7, which is clearly just 164. So now, before we move on to the probability topic, let's have a small raffle. I'll be sending the link in the chat. Okay, the prize is like 2 winners will get a free 1-hour class from Explore Math on any concept they want to learn. Okay, let's move on to counting and probability and combinations. So now, before we dive deeper into probability and combinations, we need to know what factorials are for those who don't know. So factorial is just like if you have n factorial, you multiply, that means you take n times all the integers less than n all the way to 1. Like an example is 5 factorial, which is just 5 times 4 times 3 times 2 times 1, which equals to 120. Now, the arrangements for a letter of word like is the number of letters in the word over the number of times it repeats. For example, A repeats 2 times, so you divide it by 2 factorial for that. And then P repeats 2 times, so you divide it by 2 factorial for that. This is just some basics. Let's move on to some. It'll get more advanced in the future. So now below is the way to calculate how many ways there are to choose R items from N items, where N represents the number of items and R represents the number of items that you want. There's one thing that you need to remember, that the order does not matter here. This means that if you want to choose 2 letters like from A, B, and C, then A, B is the same thing as B and A, because order does not matter here. And then there is no and then this is the way you represent it. Like if you want pretend 4 items, and for pretend you have 4 shirts and you want 2 shirts, then you take 4 choose 2. It's written in this way, which equals to 4 factorial over 2 factorial divided by 2 factorial, and then you can compute this on your own. This is just a basic example, and then we don't have an example problem for this because this method is pretty basic and we don't want to solve like a basic problem. We want to go more into the depth of the concept. So permutations. Now the only difference between permutations and combinations is that permutations includes the different arrangements of the combinations. Permutations are arrangements of the combinations. For example, there's a good problem which is how many integers from between 100 and 999 inclusive have the property that some permutations of its digits is a multiple of 11 between 100 and 999. For example, 121 and 211 have this property. Now, let's think about the problem first. For example, if we have a multiple that is, let's say 2, let's say 3, 4, 1. And then there are 6 permutations for this because 3 factorial, so there's 6 ways to arrange it. And then if we do this for all the multiples of 11, like that won't work. We can't just do that because this can be arranged as 143, which is also a multiple of 11. That means we will be over counting, which is something we want to avoid. And then there will be some cases in which you have like 440, and if you arrange this clearly, there are 2 numbers that are repeating, and there's a 0. So there are only 2 ways to arrange those numbers. So we know that 100 and 999 inclusive have 81 multiples of 11. You can calculate this on your own by saying 110 is the minimum, and you take the maximum, and then you just subtract them and divide by 11 plus 1, and then you get 81. But you need to realize that not all of them have a permutation of 6, because you can literally switch the hundreds and units digit, which brings in another multiple of 11. So we have 3 permutations for all of those multiples. So let's just say 81 times 3 is 243. But we will be subtracting. Now we're close to the answer, but we need to subtract for the numbers with 0 in them, because we know 0 can't go in the first digit, obviously. So how many multiples of 11 have a 0? Well, we need to think about that. We know 110 does, 220 does, 330 does, all the way to 990, which brings in 9 numbers. So minus 9, because they have 1 less permutation each, because 110 can't be arranged as 0, 1, 1. We know that. So minus 9. Now we have to think more. We know that what if 0 is the middle digit? Now for that to be true, the left and right digit have to sum to 11 because of the divisibility rule for 11. And in that case, this can't be 1 because 1 and 10. Obviously that's not going to work. So 2 and 9, 3 and 9, 4 and 9, all the way to 9 and 2, which brings in 8 cases. 243 minus 9 minus 8 is 226, which is our final answer. So we applied some basics of permutations, some very basics, and we found out a problem 25. Now casework. Casework is all about organizing your work into different cases to find the answer. And the most important part is reading the problem multiple times so you don't miss a single case at all. In this problem, it says rabbits rabbits Peter and Paul have 3 offsprings, Flopsy, Mopsy, and Cottontail. These 5 rabbits are to be distributed to 4 different pet stores so that no store gets both a parent and a child, and it is not required that every store gets a rabbit. Now this is the most important part, which means now there are 2 cases. Either the first case, the first case that the parents are in different the parents are in different cages, stores. And then the second case states that they're in the same store. And now we'll have to work with those cases. So for the first case, in which they're in different stores, now we want to choose 2 stores. We want 2 stores from 4, and the first one. You have 4 ways to choose the first store, and then 3 ways to choose the second store. So there are 12 ways to choose the stores that the parents go in. But after that, the children can go, and then there are 2 more stores for the others. And they can either go there, they have 2 cases. They either go here or here. And it doesn't matter if all 3 go to 1 or all 3 go to 1, because it is not required that every store gets a rabbit. But the only restriction we have is that no store gets both a parent and a child. So if we have 2 cases for each rabbit, for each child. Either he goes here or here, and that's 2 times 2 times 2. And if you multiply this is just 2 times 2 times 2 is 8, 12 times 8, which is 96. Now they're in the same stores. Now to choose the same store, there are just 4 ways to do that. And now the only difference is that now there's an extra store for the children to choose. And now there are 3 choices. They can go here, one can go here, one can go here. Pretend this guy is choosing his store. Then he can go either here or here or here. That's 3 cases, and that applies to all of them. So this is just 3 to the power of 3, and this multiplies to 27 times 4, which is 108. So our answer is just 108 plus 96, which is 204. So this shows the power of organizing our work, which made this problem pretty simple. So the next problem. This is a very basic example, but I think it's a good one to show lists and complementary counting. So complementary counting is all about counting more than what you need, then you subtract the extra amount. And it can be very useful in some situations. Usually problems that say at least, it's usually related to combinatorics and probability, and we'll have a very easy solution with complementary counting. This problem is a great example. How many subsets of 2, 3, 4, 5, 6, 7, 8, 9 contain at least 1 prime number? Instead, we can just find out the number of subsets we can make, and subtract that with the number of subsets with 0 prime numbers. And if we do that, we'll find the number of subsets that contain at least 1 prime number. And if you do that, in a subset, you have 2 choices. Either you include a number or you don't include a number. You include it or you don't include it. So you have 8 of those numbers. So that means 2 to the power of 8 is the number of subsets you have. And then there are 4 composite numbers here. 4, 6, 8, and 9. And then the number of ways to arrange these in all subsets is just 2 to the power of 4, because there are 4 terms. And 2 to the power of 8 is just 256. And 2 to the power of 4 is 16. And if you subtract those 2 numbers, you get 240. This means our answer is simply just 240. And this shows the power of complementary counting, instead of actually making cases with 1 prime number, or 2 prime numbers, or 3 prime numbers, or 4 prime numbers, but we just skip through that computation. Now this problem. Now constructive counting is like when you have lots of numbers, and then you try to look for a solution in it. And then there are lots of numbers that you have to go through, and it's very helpful in very complicated problems. And this one is a very good example. Now we want to find the number of ordered pairs of positive integers, no zeros in this, such that a plus b equals to 1000, and neither a nor b has a 0 digit. Now to find the number of pairs we have, if we disregard this fact that there is a 0 digit, we're not allowed to have that. We disregard it. for now. So we see that if this is A and this is B, and A can be 1, B can be 999, and then A can be 2, B can be 998, all the way to A can be 999, and B can be 1. So there are clearly 999 cases for that. But clearly this is not the answer, because there are more pairs that we need to get rid of. For example, we know that for a one-digit number, there are no one-digit numbers that have 0 in it, and that's pretty obvious. And then there are 9 two-digit numbers with a 0. So for 2-digit numbers, there are 9. Now, for 3-digit numbers, we have to use some casework there. So if it's in the form of x0, which means 0 is the last digit, then how many cases we have for that? Well, we have 9 choices for this first number and 9 choices for the next number. Note, I'm not including 0 for this term because x along with 2 zeros will be a separate case we're going to look at. So this is 81. And now we have the case of x and then 2 zeros. And clearly there are just 9 ways to do this, since 1 through 9 can be this first number. So this equals to 9. How about numbers in which a 0 is in the middle? Well, clearly you can have 9 numbers here or 9 numbers here, because we can't have 0 rows. It's just the same case as having 2 zeros. So clearly this is just 9 times 9, which is 81. And now this is the most important part. We know that the complement of these first 3 numbers, which means 1000 minus these numbers, will have a 0 as a units digit. What I mean is, for example, let's take this number, 100. That means whatever the other number is, like B, 900, it still has a 0. So that means we don't have to multiply this by 2. That means we will always use this as the case. However, this term needs to be counted twice, because if we have a number in this form, then the complement, which is 1000 minus this number, will not be in the form of 0, which means this can occupy A or it can occupy B. But for the other numbers, the number, if you subtract it from 1000, the other number already has a 0, so we don't overcount that. So for this, we need to multiply this by 2 to find the answer. So for this, we have 9 plus 81 plus 9, which is just 99, plus 81 plus 81, because we have to multiply this by 2, and you get 162. And then we have 999 cases from this, so we have to subtract this expression. And then after you do this small computation, you get 738, which is our answer. So this shows the power of constructive counting, because it can help you organize a math problem which has a lot of cases. Now our next problem. Maybe if you think it's geometry and you're gonna get scared because it's a 3D problem, you shouldn't, because first you read the problem and then decide if it's hard or not. So in the problem, it says, as shown in the figure below, there's a polyhedron with 12 congruent regular pentagonal faces which float in empty space with 2 horizontal faces. Note that there is a ring of 5 slanted faces adjacent to the top face and a ring of 5 slanted adjacent faces to the bottom face. Now, how many ways are there to move from the top face to the bottom face via a sequence of adjacent faces so that each face is visited at most once, and moves are not permitted from the bottom ring to the top ring? What this means is that, pretend I'm here, then I go here and I go here. I can't go back here because I can only go to each place at most once, which means either once or 0 times. And pretend I'm here. That means I can't go here or here because I'm not allowed to move above to the top ring. So this problem is actually a lot simpler than what it looks. So we always start at the top square here, and there are 5 pentagonal faces below it. So there are 5 ways to choose where he goes first. Let's pretend we go here. Wherever you land, you can either walk to the square next to it in both directions, clockwise or counterclockwise, or you can go 2 pentagonal faces, clockwise or counterclockwise, which means 2 plus 2 for 1 pentagonal face or 2 pentagonal faces. And for 3 pentagonal faces, there's still 2 ways. And for 4, you just go around the whole thing either one way or the other way, clockwise or counterclockwise. So plus 2. Or you don't even do that, or just go down immediately, and that's a separate case. So 2 plus 2 plus 2 plus 2 plus 1 is 9. That means there are 9 cases to choose what we do in the top ring. And after that, we need to decide what to do after. Now, wherever you land, it doesn't matter where you land. What matters is pretend you land here. There are 2 ways to go to the bottom ring. So that means 5 times 9 times 2. Now, if you're at the bottom ring here, now, if you realize that the number of ways we had to stay in the top ring was 9, and by symmetry, it's the same for the bottom one because there are 5 faces there. So it's 5 times 9 times 2 times 9. However, once you get to a pentagonal face at the end, there is no way to go. You can't go up here. You can't go up here. And we include it for all the cases. So that means you go down immediately, which is times 1. And for that, you get 5 times 9, which is 5 times 2, which is 10, times 9, times 9, times 1, which is clearly just 810. So the next concept, probability in simple words, is just favorable outcomes over possible outcomes. And this is just some basics for those who don't know what it is. And now let's move on to some harder problems. And you can also find casework in probability, and this is very common in questions related to probability. You use casework to find the number of desired outcomes. Then you find the total number of outcomes. So a number m is randomly selected from the set 11, 13, 15, 17, 19, and the number n is randomly selected from 1,999, 2000, all the way to 2018. Now, what is the probability that m to the power of n has a units digit of 1? So the first thing to realize is that 19999 and all the way to this has 20 numbers. And we know that this is 5. So the easiest thing to do, we're gonna take each number here and use some casework. So for 11, we notice that 11 to the if you raise it to any number, the units digit will always be 1. Test it out. 1 times 1, 1. 1 times 1, 1. You get what I mean? The units digit is always 1. That means there are 20 cases for when you have 11. 20 out of 20 all work. Now for 13, now we're going to take 13. Now 3 times 3, 9. 9 times 3 is 27. And 7 times 3 is 21. We're literally just looking at the units digit. And this cycles again and again. And every exponent that is a multiple of 4 will have a units digit of 1. So 2000 is one of those, 2004, 2012, 2016, and there are 5 of those numbers in this set. So there's an extra 5 here. And for 15, you should realize that 5 times 5 is 25, 25 times 5, it always has a units digit of 5. So there are 0 cases for that. How about for 17? Now for 17, 7 times 7, 49, 9 times 7, 63, 3 times 7, 21, and 1 times 7, 7, and this just cycles again. We're just looking at the units digit. Every exponent that is a multiple of 4 will have a units digit of 1, and it has 5 because it's the same thing as taking 13 or 17. The number of outcomes are the same, which are 5 in this case. How about 19? 9 to the power of 1 will always be 9, have a units digit of 9. 9 to the power of 2 will have a units digit of 1. 9 to the power of 3 will have a units digit of 9. So it's just cycling between 9, 1, 9, 1. So every exponent that is a multiple of 2 will have a units digit of 1. And that means there are 10 even numbers here. 10 numbers that are multiples of 2. So that means there are 10 cases for that. And in total, the number of desired outcomes we want are 5 plus 5, 10 plus 10, 20 plus 20, 40. And the number of total outcomes is just the number of terms we have here times the number of terms we have here. So 20 times 5, which is 100. And 40 over 100 is simply just 2 over 5, which is our answer. So this shows the power of like casework. Sometimes in probability, you will have to take different cases also to find the answer. And clearly we did that here, and we actually found the answer. So the next problem, without loss of generality, it's actually very important to know because sometimes it is good to assume values instead of substituting variables, especially for probability. It's because the values won't affect the problem. Also, it can be used only if the values you're substituting don't bring in new restrictions. So this problem is a great example. So when rolling a certain unfair six-sided die with faces number 1, 2, 3, 4, 5, and 6, the probability of obtaining face F is greater than 1 over 6. And the probability of obtaining the face opposite is less than 1 over 6, and the probability of obtaining any one of the other four faces is 1 over 6, and the sum of the numbers of opposite faces is 7. Now this tells us that if one face is 1, then the opposite to that is 6. Then if this one is 2, then the opposite is 5. If this one is 3, then the opposite is 4. Now, it says when two such dice are rolled, the probability of obtaining a sum of 7 is 47 over 288. Given that the probability of obtaining face F is m over n, where m and n are relatively prime, we want m plus n. So let's say that face F is this x. 6, yeah. And let's say the probability of rolling 6 is just 1. We know that the probability of rolling 1 will be 1 over 3 minus x, because the rest of these have a probability of 1 over 6. That means 1 minus 4 times 1 over 6 brings in 1 over 3. So that means 1 over 3 is the sum of the probabilities of this. So if this has a probability of x, then this has a probability of 1 over 3 minus x. Then now we will use some basic algebra. We know that this has a probability of 1 over 6 and this has a probability of 1 over 6. So that means if you multiply both of those cases, you get 1 over 36. However, we have 4 of those cases, 2 and 5, 3 and 4, and then 5 and 2 and 4 and 3, because you can flip those over depending on which dice you get the 4 and 5 on. 4 and 3 or 2 and 5. So it's 1 over 36 times 4, which is 1 over 9. And now you subtract this from the total probability, which is 47 over 288. 47 over 288 minus 1 over 9. And after this, if you compute this with the LCM, you have 15 over 288. And then this reduces to 5 over 96. This means the probability of getting 1 and a 6 will be 5 over 96. Now using that, we know the probability of rolling 1 is just 1 over 3 minus x. And the probability of rolling 6, the complement, in this case, is x. However, there are two cases because either one dice can get 6 and 1, and the other can get 1 or 6. So you multiply this by 2 after, so just write this 2x over here. And this equals to 5 over 96. Now let's try to solve the problem. So if you expand this, you get 2x over 3 minus 2x squared equals to 5 over 96. Clearly you can multiply both sides by, because we don't want this messy expression here. We'll just multiply it by the denominator 96 to get 64x minus 96 times 2, which is 192x squared equals to 5. And now let's simplify this. And after you simplify this, you get 192x squared minus 64x plus 5. Now to actually after you factor it out, you get let's factor this out. So we know 192x squared, it's 2 times 96. We need to find a pair such that if you multiply it by 5, then you can also get 64. I'll just factor this out for you guys. Yeah, okay. 8x is over here, and 24x is here. And you multiply this by -1 and -5. And this is 24x. And after you compute this, and this equals to 0. So x has to equal to 1 over 8, or x equals to 5 over 24. And clearly, remember the restriction we had at the beginning, that the face f is greater than 1 over 6. Clearly, 1 over 8 is not greater than 1 over 6. We don't care about this. Which means the probability is 5 over 24 because we took at the probability of ruling f as x. And now we found it. It's 5 over 24. And we want the denominator plus the numerator, which is 5 plus 24, which is 29. Now let's move on to the next problem. Now for infinite combinatorics and probability, like usually you like look for problems, like you count them, and then you might just have infinite values which are never ending. In that case, you look for a pattern and then you apply the infinite geometric series sum, which we learned before. Okay, so in this case, the problem says Tom and then his friends like Harry and everyone are playing a game starting at the same time, and each of them flip a fair coin repeatedly until he gets his first head, at which point he stops. Now we want to know the probability that all three flip their same coins. Flip their coins the same number of times to get heads. So let's say they get heads in the first try. For all of them to get a head in the first try, the probability is 1/2 to the power of 3. How about for the second try, in 2 tries? For them to get heads in 2 tries, the first try needs, for the first try they will all fail. So the probability that they will all fail is just 1/2 to the power of 3. Then you multiply this to the probability that they'll all succeed, which is 1/2 to the power of 3. And in this case, we can clearly just add the exponents to get 1/2 to the power of 6, because we do not care what they get in the first try, and there's just a half probability of each case. Now for the third, if you want it in 3 tries, it'll take for Tom to get it in his third try, he will fail for the first try. There's a 1/2 chance of failing. Then there's a half chance of failing again, and there's a half chance of being successful again. And the same applies for all 3 of the people. And you raise this to the power of 3. And if you notice, 1 over 8 is the same thing as 1 over 2 to the power of 3. And we also raise this to the power of 3. And if you remember the exponent properties that we learned, you just multiply these exponents to get what we want. So 1/2 to the power of 9. And remember what I said, if you look for a pattern and it keeps on happening again, it's most likely gonna happen for the whole time. So we know the sum, and we see that the whole time this is just being multiplied by 1 over 2 to the power of 3, which equals to 1 over 8. And that means the first term is, this is the first term, 1/2 to the power of 3, which is 1 over 8. And you divide this by 1 minus the ratio, which I just calculated, 1 over 8. And this is 1 over 8 divided by 7 over 8. And if you compute this, you get the 8's cancel out, and you just get 1 over 7, which is the probability, which we found using the infinite geometric series, which shows that those algebraic concepts apply even in combinations and probability, which makes algebra the base of competition math. Now the next problem, geometric probability. Whenever your number of combinations, you can't count them. That's perfectly fine. It's because there are because the number of combinations you have are infinity. And then the only thing that can measure infinity is geometry. That means if you have an infinite number of cases, you use geometry and you graph it out. So it says real numbers x and y are chosen independently and uniform at random from the interval of 0 through 1. And which of the following is closest to the probability that x, y, and 1 are the side lengths of an obtuse triangle? Okay, now for this problem, clearly we can't calculate it because one side can be 0.01, it can be 0.0001, it can go on, it can be anything. So do you get what I mean? There's an infinite number. So clearly, trying to solve it by hand is like impossible. So that means we have to graph it. So let's get graph paper out now. Okay. So now since we have graph paper out, let's just draw a square, and let's say this is 0, 0, and this is 0, and this is 1, 0, and this is 0, 1. And we know this because it's from the interval of 0 and 1. So we're not going to graph it all the way to 1000 or 2. We're just going to graph it to the max numbers that we can have. And then it just makes the square. And after this, now we're going to use some geometric relationships. So it says, which of the following numbers closest to the probability that x, y, and 1 are the side lengths of an obtuse triangle? Now for this to be an obtuse triangle, two of the side lengths, if you get the sum of it, it has to be greater than the third side. So pretend we take the two side lengths of x and y. That means x plus y has to be greater than 1 because of the triangle inequality. Now to graph x plus y is greater than 1, you can simply first graph x plus y is equals to 1, which is this line here, which is just the diagonal of the square. And then the region we want is this, it's this whole thing, because if you add any numbers here, any of x and y numbers in this region, then it will always be greater than 1. And now we have another case. Now using the Pythagorean inequality, the Pythagorean inequality states that the longest side of a triangle, which in this case it's clearly 1, is going to be the longest. So 1 squared has to be greater than x squared plus y squared, because of the Pythagorean inequality, which states that the longest side of the side opposite to the obtuse angle, like pretend this is an obtuse triangle, and this is the obtuse angle, and this is side C, this is A, this is B, then it states that c squared is greater than a squared plus b squared, and it's the same case here. But the only thing is we know that c is the longest side. So now we need to try to find the answer. So now we need to graph 1 is greater than x squared plus y squared. And this can be done by setting 1 equal to x squared plus y squared. And we know that this is just the graph of a circle. And if you graph the circle, you'll get a quarter circle with the radius of 1 over here. And now the problem seems a lot more solvable. And since we want 1 has to be greater than x squared plus y squared, we know that anything in this region will work. But it also has to be in this area also, which means it has to be the intersection, which is this. And this can be found by taking the area of the quarter circle and subtracting the area of the triangle here. So the area of the quarter circle, clearly, it's pi r squared, and the radius is 1. And then you divide by 4 because it's a quarter circle. So pi over 4 minus the area of the triangle, 1/2, times base times height, which is just 1 over 2. And that is the probability. Now you can compute this as, because pi is 3.14, and if you divide it by 4, you'll get about like 0.79, I think. And 1 over 2 is just 0.5, obviously. And if you subtract these, you get 0.29. So this is approximately our probability. And the question from the test, this problem 22, it asked for the approximate probability. And we found it using geometric probability. Now this brings in another important concept, which is the honey stick identity. And now below, this is the problem that we're going to solve. And the honey stick identity is very helpful because it can help you simplify very complicated looking expressions and actually simplify them into something a lot shorter. So it states that if I'll just give you an example since it's a lot easier to understand. So if we have 2 choose 2 plus, like, let's say 3 choose 2, plus 4 choose 2, then the honey stick identity tells us that this is equal to 5 choose 3. So then obviously it's a lot easier to find 5 choose 3 instead of, I meant the hockey stick identity. Yeah, hockey stick. Yeah, so hockey stick identity. So instead of like finding each individual 2 choose 2, 3 choose 2, plus 4 choose 2, instead just find 5 choose 3. It's a lot easier, trust me. Now for this problem, it says given that 1 over 2 factorial times 17 factorial plus 1 over 3 factorial times 16 factorial, and it keeps on going on and on, and it equals to n divided by 1 factorial plus 18 factorial, and we want to find the greatest integer that is less than n over 100. Now the problem looks pretty scary, but in these cases they're obviously not going to give you a problem that is unsolvable. So you look for a pattern and you notice 2 plus 17 is 19. 3 plus 16 is 19. 4 plus 15 is 19. 5 plus 14 is 19. 6 plus 13 is 19. 7 plus 12 is 19. 8 plus 11 is 19. 9 plus 10 is 19. And 1 plus 18 is all 19. Which means if you multiply both sides by 19 factorial, maybe we can get something good. So I'll just write it here, because plus 19 factorial plus 19 factorial, since I'm multiplying the whole thing by 19 factorial. And then now you should start to see a pattern now. So now this is obviously this 19 factorial times n just becomes 19n. So now if you notice this, 19 factorial divided by 2 factorial times 17 factorial is literally just 19 choose 2. And 19 factorial over 3 factorial plus 16 factorial is just 19 choose 3. And now I'm not going to write all of these down. I'm just going to skim through to 19 factorial and we choose 9 factorial. Now the trick here is to realize that the sum of 19 choose 0 plus 19 choose 1 all the way to the end, all the way to here, is actually half the sum, because we see that this term equals to 19 choose 19 and this term equals to 19 choose 18, and then this term equals to 19 choose 10, which means by symmetry, if we find the sum of 19 choose 0 all the way to 19 choose 19 and divide that by 2, we'll actually have the sum of this entire, this enormously large number. And clearly, using the sum of a Pascal's triangle, pretend if we have like n of squared minus 20, and that is the answer. And then we don't have 512 squared. Just calculate that and subtract 20. And I just use the calculator for this part. So 262,124. This expression equals to 262,124, and you want to divide this by 100 and find the greatest integer that is less. And clearly, if you divide this by 100, we have a decimal point here. And then first we divide this by 19, and 262 and 124 divided by 19 is we get 13796, and if you divide this by 100, you get 137.96. But it says the greatest integer less than 137.96, and clearly that's not 138, since that's more than 137.96, so it's 137. I had to use a calculator at the end, but if you're taking the AIME, then it's fine even if you have to compute 512 times 512, because you have so much time to calculate it. That's why it's perfectly fine even if you have to. Now, the binomial theorem. Now, the binomial theorem is it's very useful if you have like a plus b and you want to find it to a huge power. And like pretend a plus b squared. If I rewrite this using the binomial theorem, then using this is just 2 choose 0 times a to the power of 2 times b to the power of 0 plus 2 choose 1 times a to the power of 1 and then b to the power of 1 plus 2 choose 2 times a to the power of 0 times b to the power of 1. Notice that the exponents for each a term slowly goes down, while the exponent for the b term slowly goes up. That's one thing that you should remember. Oh, this is actually 2. And remember that the sum of the exponents will always be the same thing. So if you want to check if you're correct, just look at the sum. And clearly, 2 plus 0 is 2, 1 plus 1 is 2, and 0 plus 2 is also 2. So 2 choose 0 is just 1. So a squared. And b to the power of 0 is just 1, because anything to the power of 0 is 1. So a squared plus 2 choose 1 is just 2, and a and b, plus 2 choose 2, which is 1, and a to the power of 0 is 1, so a squared plus 2ab plus b squared. And we used the binomial theorem to find this out. And you can do the same thing even if you have a higher exponent. And now this is a problem which is a very good example of the binomial theorem. And this problem involves some number theory and combinatorics. So if you remember from yesterday's class, you remember that to find the hundreds digit, this is impossible. 2011 to the power of 2011 is monstrously large. But if you do this in mod 1000, you'll get 11 to the power of 2011. Because we don't need to find the whole thing, we can just make something that's a bit smaller. We can just calculate this in mod 1000 to get the last 3 digits. Because even if the number is like 2999, in mod 1000 we have the last 3 digits, and we want the 100. So in any case, we'll find it using mod 1000. Maybe you could do mod 8 and mod 125 and use the Chinese remainder theorem to find the answer. But that is just way too complicated. But using the binomial theorem is a very, very, very easy way to find the answer to this problem. So using mod 1000, we know that the hundreds digit of 2011 to the power of 2011 is equivalent to 11 to the power of 2011 in mod 1000. Now using a clever application of the binomial theorem, this equals to 10 plus 1 to the power of 2011 in mod 1000. Now this, we're obviously not going to compute each term using the binomial theorem, but you'll see what we're going to do. So using the binomial theorem, we know that 2011 choose 0 times 10 to the power of 0 times 1 to the power of 2011 plus 2011 choose 1 times 10 to the power of 1 times 1 to the power of 2010 plus 2011 choose 2 times 10 to the power of 2 times 1 to the power of 2009. Now, I want someone to answer in the chat why I'm not going to write 2011 choose 3 times 10 cubed and go on. I want someone to know why we're skipping through that. Yup, a person in the chat was able to answer why we're skipping through it. They're perfectly right. Because in mod 1000, anything that is a multiple of 1000, obviously, if you divide it by 1000, it just cancels. It just cancels out. And the whole thing, oh yeah, I accidentally wrote divided here. So yeah, it just cancels out. That's why we don't write, we don't go further. And we're done here. We know 1 to the power of 2011. That's just 1. 10 to the power of 0, that's just 1. And 2011 choose 0 is just 1. So this complicated looking thing, it brings in 1. Plus, now we're going to calculate the next term. 2011 times 10 to the power of 1. It's obviously 20,110. And the 1 to the power of whatever number, it's always going to be 1. So we have to add this to 2011. So I'll make some space for this. Since it's in mod 1000, we can convert it later. So 2011 times 2010 divided by 2. This is the same thing as this choose 2 expression times 10 squared. Notice that we're calculating in mod 1000, so we can rewrite this as 11 times 10. So what we're finding is 11 times 10 divided by 2, which is clearly just 55. 55 times 10 squared, which is 550. And now adding these expressions up, you get we have 20,000. You can just mod 1000 here before adding it, but we'll just add it so it looks simpler for the people watching. So 0 plus 0 plus 0, 1. 5 plus 1, 6. 5 plus 1, 6. And then we have 20,661. And if you divide this by 1000, the remainder is just 661. but we want the hundreds digit, which is 6. So this shows the clever usage and how we applied the binomial theorem here to find the answer, which was the hundreds digit of 2011 to the power of 2011, the monstrously large number. And this shows that the binomial theorem is very important to know. Now we're almost done. Now I'm going to tell you guys some test taking strategies. Well, for each question, you get 1.5 points for blank questions. So if you don't know the answer to a question, or you think you're not going to get it, then it's better to leave it blank. And your goal should be to eliminate answer choices if you're able to eliminate a decent amount and then guess the answer. But that's only if you can actually eliminate some. And most important of all, you should try all the problems. You're trying to battle the problems, not the problem number. A lot of people look at the problem number and say, okay, this is a problem 25. I am not solving it. That you don't think in that mindset. You should at least read it and try to solve it, and maybe you'll actually get the answer. Because in the final 5, there are actually some problems that are they're like 2. There will be 2 problems there, 1 to 2, or even 3 sometimes, that are a lot easier than what it looks, and you can actually solve it with some basic knowledge and some practice from before. So if you read it, then you might get some extra points instead of just skipping it because the problem number is 25. So don't ever think in that mindset. Now, I'm very happy. Thank you guys for watching. And now please subscribe for more seminars and videos in the future. Now the 40-page handout will be sent in a few hours.